today we're going to look at just a summary of addition of vectors. And remember, depending on the form that the vectors are given in, sometimes it's very, very easy to add the vectors, and sometimes we have a little bit more work to do. So remember, if we have two rectangular form vectors or component form vectors, then we would actually have their x, y coordinates for our vector notation. And if we have component forms or rectangular forms, the addition is very simple. We do add the vectors head to tail. I drew a little diagram here. If this was vector over A and up B, graphing it in standard position, attaching vector CD tail to the head of the previous one, I made this look like the x component is positive and the y component is negative, and then I have my resultant vector. And I just simply add the x components together and add the y components together, and I'll have my resultant vector. And it actually will make sense in the picture. Here's a little numerical example. If I had vector 3, 4 over 3 and up 4, added to it is vector negative 5, 6. So at the head of the first vector, I went over 5 to the left and up 6. I can see that my resultant vector is this one that I have in blue from the beginning to the end, and I can see a left movement of 2 and an upward movement of 10, and if I add these coordinates together, I'll get exactly that. So rectangular forms are simple. Common form or polar form, remember, are going to take a little bit more work. If I ask you to do the addition specifically using these forms, you will have to use some trig. And the gist of it is, draw your one vector. I know the magnitude is A, and I gave the first angle as theta sub 1. And I have it as a bearing since I was in a common form vector. And then from the head of this vector, I make another little coordinate system. And I have a vector here that is B in magnitude. So its length would be B units long, and then the angle as a bearing would be theta sub 2. And I just made an arbitrary angle of theta sub 2. You will always be able to calculate the angle that is formed between these two vectors. You will always be able to do this with piecing together the values that are given. You may be using some corresponding angles, a little subtractive process, but you always have enough information to determine this angle. And when you do, you have a side and an angle and a side, which will allow you to be able to use law of cosines to find the magnitude of the resultant vector. And so I could use law of cosines to find this, and then I have a choice as far as determining this final angle here, as I labeled it as theta sub 3. This would be the bearing of that vector from the north to the direction it's pointing, and I would always be able to use like a law of sines or possibly a law of cosines in order to determine this part of the angle, which in turn I could do a little bit of arithmetic and some analysis to determine what the final bearing is. Okay, so a little example here is if I gave you two vectors in common form, and again this would work just as well if I gave these in polar form. But if I have this first vector of 15 miles, 60 degrees, from north I measured over 60 degrees approximately and went out 15 miles. And then at the head of this vector I put a little new coordinate system, and I have a magnitude of 18 miles with 100 degrees. So I know I have gone from north 100, so I've gone 90 plus 10. So this little acute angle here is 10 degrees. And as I said on the previous page, you always have enough information to find that angle. You just have to do a little bit of constructing. If this is 60 degrees, here's a north-south line, another north-south line. This angle has to be 60 degrees as well because they're alternate interior. Now, if this angle is 100, and I know that this is a straight angle, I can figure out a few different ways that this is 80 degrees. So this large angle I have here is 140 degrees. And this is my resultant. I'll draw it in blue. And that's the vector I would need to find. So I can use law of cosines to determine this length. I'll just label it as x. So I would know that x squared would equal 15 miles squared plus 18 miles squared minus 2 times 15 miles times 18 miles times the cosine of the included angle, and the cosine of the included angle is 140 degrees. Check the mode on your calculator. I've got mine here off to the side. And a little quick calculation. Double check, make sure you type things in properly before you hit enter. Looks like I have. And I'll square root that answer to find the x length. So I have the magnitude is 31.03 miles. And that's rounded off. Now I would just store that value real quickly. Store it as alpha A, alpha x, whatever the choice is. I stored it as alpha A, so I'll put a little a up above. And now at this point, I need to find another angle in order to get this back into a common form vector. So I'm going to calculate this angle right there. I'm going to set up a law of sines. I know it's an acute angle. I already had my obtuse angle being used. So if I set up a law of sines, I know that the sine of theta is to its side opposite as the sine of 140 degrees is to its side opposite. And that side opposite is at 31.03 miles, which I've already stored. So I know I need to take 18 times the sine of 140 degrees and divide that by the value that I have stored. And that will be the sine of my angle, inverse sining that. And I get that angle theta is 21.9 degrees. I haven't found the bearing yet, but I'm almost there. I know that my vector has a magnitude of 31.03 miles. And I know that I have a bearing here of 60 degrees plus my angle. So that will give me 81.9 degrees. So now I have my angle in common form. If I needed to change it to a rectangular form, I could definitely do that as well. But I have added angles, or added vectors that were in common form, and added vectors that were in rectangular form.